Okay, so step 1 we have seen finding the order of the filter. I will take up a challenge. We'll see how to design analog Butterworth filter, okay, which has minus 2 dB pass band attenuation at 20 radians per second, and at least minus 10 dB attenuation, stop band attenuation at 30 radians per second. Okay, now with respect to this problem, step 1, what we have seen in the last session, okay, you need to find the alpha p, alpha s, and omega p and omega s. So in this challenge everything is given very explicit. So this is my pass band attenuation because it's a lower frequency, so 2 dB, and alpha s is 10 dB, omega p is 20 radians per second, and omega s is 30 radians per second. Okay, so once we know these values, we can directly substitute in the formula log of square root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 divided by log of omega s by omega p. Okay, so we can directly substitute the values. Log of square root of 10 power alpha s is 1, so 10 power 10 minus 1 by 10 power 0.2 minus 1 by log of 30 by 20. Okay, so which gives me, if you solve this, it will come around n is greater than or equal to 3.37. so we can take it as n equal to 4. That's the first step. Okay, now the second step in designing this, okay, you need to find the poles of the transfer function. To find the poles of the transfer function, you have to use this formula sk equal to e power j phi k, where again phi k represents pi by 2 plus 2k minus 1 pi by 2n, where k takes the values from 1 comma 2 up to n. Okay, so in our case n equal to 4. So first we will find phi 1. So phi 1 is equal to pi by 2 plus k, I am substituting 1. If I substitute 1, it is 2 minus 1 1, n is equal to 4, so it becomes pi by 8, so it is 5 pi by 8. Okay, similarly phi 2 is equal to pi by 2 plus 3 pi by 8, which becomes 7 pi by 8, and phi 3 is equal to pi by 2 plus 5 pi by 8, which gives you 9 pi by 8, and phi 4 is equal to pi by 2 plus 7 pi by 8, which gives you 11 pi by 8. So once we know the values of phi 1, phi 2, phi 3, we need to substitute that into our S1. Say S1 equal to e power j phi 1, that is e power j 5 pi by 8, so which we can write it as cos 5 pi by 8 plus j sin 5 pi by 8. So if you solve this value, it comes around minus 0.3827 plus j 0.9239. Okay, in a similar fashion, if you solve for S1, S2, S3, S4, you'll be getting S1, I'll again rewrite it, minus 0.3827 plus J 0.9239. S2 will get minus 0.9239 plus J 0.3827. Interestingly, you will get S3 as minus 0.9239 minus J 0.3827 and S4 as minus 0.3827 minus J 0.9239. So as you guessed correctly, these are all complex conjugates. This is a complex conjugate of this and this is a complex conjugate of this. Okay, so whenever you have a complex conjugate, okay, we can form, so based on the poles, so step 2 was finding the poles. So step 3 is finding the transfer function. So how to find the transfer function? Nothing but you have to couple all these poles. Okay, so since these are all already as available as complex conjugates, you can easily couple them. Maybe I'm coupling the S1 and S4 root as S plus 0.3827 whole square plus 0.9239 whole square. Okay, this is the way we combine S1 and S4. Similarly, I can combine S2 and S3 roots as S plus 0.9239 whole square plus 0.3827 whole square. So combining both of these things, I can write it, I'm just expanding and writing it, S square plus 0.7653 S plus 1 and S square plus 1.847 S plus 1. Okay, I have got the denominator function. Now based on this I can write the transfer function. So my transfer function is H of S is equal to 1 by S square plus 0.7653 S plus 1 into S square plus 1.8477 S plus 1. Okay, so whatever we have obtained this transfer function, it is nothing but a normalized transfer function. We took n equal to 4, we found the 4 roots, based on that we have found. Okay, so for this transfer function omega c is 1 radians per second. So now we have to find the original cutoff frequency, that is our step 4. Step 4 is finding the real cutoff frequency omega c. So the formula for omega c is equal to omega p by 10 power 0.1 alpha p minus 1 whole power 1 by 2n. Okay, so if you substitute the values, omega p is already given in the question itself, it is 20 radians per second, and alpha p is 2, so 10 power 0.2 minus 1 whole power 1 by 8 because n is 4, so you find the value as 21.3868. okay, so this is how we find the real cutoff frequency. Once we know the real cutoff frequency, the problem becomes very simple. Already we have got a normalized transfer function H of S. In the normalized transfer function H of S, substitute S by omega c. So we have got our omega c, it is 21.386. So take our H of S function. Already we have calculated the H of S function. This is our H of S function. Wherever you have S, substitute S by 21.368. So it is almost like 1 by S by 21.386 whole square plus 0.7653 into S by 21.386 plus 1 into again S by 21.386 whole square plus 1.8477 S by 21.386 plus 1. Okay, this you have to reduce it, that is 21.386 whole square. So 21.386 whole square is 457.104 say. Okay, so this becomes your numerator divided by S square plus 16.368 S plus 1 into S square plus 39.517 S plus 1. Okay, so this is our transfer function. This is our final transfer function. So it includes 5 steps. First step is finding the specifications. From the specification we have to find the order of the filter. Once we know the order of the filter, find out the poles. Okay, so use this formula, find out the poles. Once we know the poles, step 3 is finding the transfer function. You need to combine all these 4 poles into an equation, and from that you can find what is your h of s. Whatever h of s we have found out, it is for omega c of 1 radians per second. Okay, once this is over, step 4 is finding the original cutoff frequency. To find the original cutoff frequency, you can use a formula omega p. This formula we can also take it as omega c, here also omega s, that also it's correct. Okay, so once we get this value, this is our correct cutoff frequency as per the specifications given in the question. Now in our original h of s, wherever we have s, substitute s by omega c. That will give our original analog transfer function. Okay, this is how you design a analog low pass Butterworth filter. Okay, thank you.